and this section of the class is going to talk about differentiation formulas, or at least the basic differentiation formulas. Now, in the last section, we conceptually talked about what is a derivative and why do we care, okay? In this section, we're going to move a little bit deeper, just a hair, and we're going to explain and work through some problems where we actually use some of the what I call the bread and butter of calculus. It's if I give you a function, how do you take the derivative, which, as we just said, was the slope of the line tangent to the curve, the slope of the curve, basically, okay? The rate of change. So let's just dive right into it, and we're going to do this, mainly through immersion, through examples. The first thing, I just wanted to review some basic things that we talked about from the last section, and that would be, namely, that the derivative of a function x is denoted by this prime here, the derivative, which is the slope of the line tangent to a point on this curve, okay? You can write it that way, or you can write it, as we said in the last section, as simply df dx. Now this means I'm taking the derivative of the function f with respect to the function x. It just means I'm looking at how f changes at a point. I'm looking how it changes with respect to how x changes. It's kind of like that rise over run thing. You've got to compare it with how x changes so you can sort of judge the slope of the thing. Okay? So that's sort of the basic thing. Now, as we go through here, I'm going to write a few kind of properties on board, properties of the derivative over here, and I'm going to try to leave them up for the most part, and we're going to work some problems over on the other side over here. Okay? So the first one is the derivative with respect to x, you can write it as d dx here, is like almost like a fraction, of a constant, that's what c means, is 0. That's kind of like a property, okay? What does that mean? Well, it means, remember the definition of a derivative. Derivative is the slope. How fast does something change? What's the slope of it, okay? Is it like this? Well, a constant, by definition, a constant is a constant with respect to x. If it's a constant with respect to x, it has no slope. Therefore, the derivative must be 0. So that's something you're going to remember as you work problems. The derivative of a constant is 0. It's just one of those things like in, when you're 5 years old, you learn 2 plus 2 is 4. Well, that's the way it is. Well, the derivative of a constant is 0. It's a basic thing you're just going to have to remember. And you will remember because I promise you'll be doing it all the time. So an example of that would be, let's say f of x is equal to 5. This is a function, a very simple function. Well then, the derivative of f of x, which is the same thing as saying df with respect to dx, the derivative of f with respect to x is just a big fat 0, because the derivative of a constant is 0. So that's an example related to that property. Now what if we had the derivative, again, with respect to the independent variable x, of something a hair more complicated? What if we had a constant times a function of x? What would that equal to? You're not supposed to know the answer to these, by the way. I'm just asking rhetorically. These are things that are given to you as a theorem in your calculus book. This will be equal to the same constant c times df dx. Okay? So what it means is, if you're taking the derivative of some quantity that's like a number times a function of x, well then you just pull the number out, and then you take the derivative of the function, and that's what it is. This can look kind of messy, but let's do an example to kind of illustrate what that means. If I had f of x is equal to 5x, okay, then if I were going to take the derivative, remember here I have a number times a function of x. So I can pull out the number, I'm pulling that out, and then what's left over will be the derivative of x. So I pull out the number, and then I take the derivative here, and then this is the answer. Now, I have not told you how to take the derivative of this yet, so I'm not going to give you the final answer, okay? But in the end, you pull the number out, and whatever's left over, you take the derivative. I promise you, you will not have to end up memorizing these properties, these particular properties, because they will become second nature. But I'm just explaining to them so that you get the full story. Here is probably the absolute most useful thing you'll learn for these properties, or I wouldn't say most useful, the most commonly used, okay, method to take a derivative. This one, you need to sit up and pay attention. You'll use this hundreds of times during the course of the class here. If you're taking the derivative of x raised to some power n, which n is in this case is a constant, so this could be x squared, x to the third, x to the fourth, x to the minus fifth. It could be anything up here in the exponent as long as it's negative or positive. It doesn't even have to be a whole number. It could be a decimal up there. Okay, how do you take the derivative of that? Well, it's going to look complicated, but it's very simple. You take the exponent, you put it down in front, and then you write x to the n minus 1. So in order to take the derivative of x to the nth power, you just put the exponent down here and put x down and n minus 1. If you were to really want to understand why that's the case, you'd have to spend some time looking at how that's derived. I don't plan to do that. You can go back to the definition of the derivative that we just talked about in the previous section. You know, the thing I told you that you probably won't use very much. What it's really useful for is to prove stuff like this, okay? My goal in this course is not to derive everything. I think the book's job is to do that. My job is to tell you what the results are and show you how to solve problems, how to use the stuff, okay? This is how you do this. Let's do a problem. This will become very clear here in just a second. What if you have f of x is equal to x squared? This falls in this category because it's x raised to the power of 2. Then simply f prime of x, which is the derivative, is 2, I'll pull the exponent down, times x, and in the exponent I have 2 minus 1, which is just like this, which is just 2x, because 2 minus 1 is 1, x to the 1 is x. So all you do is you take the exponent, you pull it down, you write x, and then in the exponent it's just, in this case, 2 minus 1, which is 1. So that's the answer to that. Another one, just to practice it, if you have f of x equals x to the minus 3, then how would you take the derivative? F prime of x equals, take the exponent, in this case negative 3. Here I'm going to put parentheses around it just to be clear. It's negative 3 times x to the negative 3 minus 1. It's the same formula. Negative 3, you subtract 1 off. So you'll get negative 3 x to the negative 4. Okay? Easy. Easy, 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 right? Basically, what I'm teaching you how to do is to take derivative of polynomials. This is how you take, this is going to be how you're going to end up taking derivative of any of those polynomials that you've ever worked with. X squared plus 3x plus 2 plus 5. Okay, things like this. But just to do a couple more quick examples, if g of x is equal to 2 times x to the 5 power, then dg dx, the derivative of g with respect to x, is going to be, using this first property, it's 2 times a function of x, so I just write 2 down, because I can pull the 2 out, and now I just take the derivative of this part, x to the 5. So it's going to be times 5 x to the 5 minus 1, okay, which is 10x to the 4th. So really all I did is I moved this 5 down. It's got to get multiplied by this 2, which gives me the 10. In the exponent here, I've got 5 minus 1, which gives me a 4. The only difference between this and the previous problem is that I had a number out here. And technically, you're going to have to use this property to remember that this number just sort of stays out there, and I'm multiplying by the derivative of this, which ends up being 5x to the 4th power. When you multiply, you get 10. Now, at the end of the day, you won't ever have to think about using this property. It will become second nature. But this is the rigorous way in which you do it. What if you had g of x is equal to 3x to the negative 4th power? Well, then g prime of x is simply going to be 3, just stays out front, just like this tells you, times. Exponent comes down, negative 4th, and then in the power of x, I've got negative 4 minus 1. So then I've got 3 times negative 4 is negative 12, x, and then the exponent, I've got negative 5. Negative 4 minus 1 is negative 5. So those are some properties there. Okay? Very, very useful properties. Now, what follows is going to be a couple of properties that are going to seem a little goofy, but you need to formally be aware of them. If you have a function f, this could be a function of x, plus a function g, okay? So it's a sum of two different functions, okay? Functions of x, let's say. And you take the derivative of that sum. That's just equal to the derivative of f plus the derivative of g. So anytime you have two functions here, you take the derivative of each one separately, and you add them up. Similarly, if you have function f minus a function g, and you take a derivative, it's just the derivative of f minus the derivative of g. You might say, when would I ever use that? I mean, who cares? Well, this is what I meant when I told you that these things are going to be very useful for you to be able to take derivative of polynomials. Okay? What if you have f of x is equal to x squared minus 10x plus 100? And I say, find the derivative with respect to x. Well, I'm taking the derivative of this whole thing, which is a sum of functions of x. I mean, there's no x here, but you really have an x to the 0 power here, okay? So what you do is you just take the derivative of each thing individually and you add them up. And that's fine. And you have the tools to do that because I've shown you how to take the derivative of these things. So what you'll have for this first one is just 2x. 2 comes down, x. And then in the exponent, it's 2 minus 1, so that's the derivative there. For this one, you're going to have simply 10. And let me explain why real fast. It may not be clear. 10x, negative 10x, is really 10x to the 0 power. I'm sorry, 10x to the 1 power. Okay. So when I take the derivative, I pull the 1 down, and it's times negative 10, which gives me negative 10. X to the 1 minus 1. I got to subtract 1 off in here, which then becomes negative 10x to the 0 power. And anything to the 0 is just simply 1. So I'm left with negative 10. Now, I did that so fast in my head because, as I told you, you will get very good at doing this stuff. Okay? So, 2x to the 1 power, 10x to the 0 power here, which is just simply 1. And then we just said the derivative of a constant is 0 because constants don't change. So I have a 0 there, so I'm not even going to write it down because 0 doesn't contribute. So this is the derivative, 2x minus 10. You know? So, you know, I'm not going to plot these, but if this function is something like this, then the derivative is going to be, you know, some function that's going to represent the slope of the tangent line of that top function there as you move along x. So what you end up with when you take these derivatives is a function that describes the slope of this curve at every point x. You plug in a point x, you get a slope. You point in another point x, you get another slope. And what you're getting is the slope of this original curve. What if you had v as a function of r is 4/3 pi r cubed. And this, in fact, is the volume of a sphere, 4/3 pi r cubed. As you change r, obviously, the radius, the volume gets bigger, right? As it goes by the third power. So the derivative of the volume, how does the volume change with respect to changing the radius? That's what we're finding here when we say, what's the derivative? What is the change in the volume as compared to the change in the radius? That would be, these are constants, so they just hang out in front. 4/3 pi, they both just hang out in front. You don't do anything with them. Times 3 comes out of the exponent, r, and then here you got to subtract 1, so you have a 2 in the exponent there. Now this 3 cancels with this 3, so what you have is 4 pi r squared. Okay? Now what if you had a problem like f of x is equal to 16x to the third power. You know, all wrapped up here in the exponent. Well, the way I would tackle that is I would say, well, that's 16 to the third times x to the third, right? Because when you have an exponent outside, you just kind of distribute that exponent in. Now, when you do that, you'll take the derivative here, and what you'll have is 16 to the third power is just a constant, times 3, which comes out of the exponent, and then you'll have x squared left over because you'll have x and then 3 minus 2 is 1, taking that derivative there. And when you put this in your calculator, the derivative of f is 12288x squared. So some big number times x squared. I'm just trying to show you that sometimes they'll write problems in such a way that it won't be exactly like what you're used to seeing, and you'll have to beat it into shape in order to be able to apply some of these things. Now, I'll go ahead and do one more quick example of how to apply these particular formulas here, and then I'll go on and I'll teach you another one. What if you have g of x, and that's equal to x squared plus 1 over x squared? And they say, what is g prime of x? Okay. That's what you're trying to find. What is g prime of x? Well, first thing you're going to look at and say, well, I know how to take the derivative of this because I can just use this. But how do I do that? That looks totally different. Well, simply rewrite it. You can write it like this: x squared plus x to the minus 2. Remember, anytime you have a negative exponent, it's like saying 1 over x raised to the same exponent. So here I've just rewritten the function. And that suits me just fine. Okay? So in order to find g of x, the derivative of g of x, what you would have is, for here, 2x, 2 comes down, x raised to the 2 minus 1 power gives me this, plus minus 2 comes out of the exponent times x to the minus 3. This minus 2 minus 1 gives me minus 3. So in the end, I'll have 2x minus 2x to the negative 3. And that will be my derivative. Okay? Good. Now let me go ahead and teach you some more properties, because these properties are crucial to really being able to take derivatives. What if you had a function f times a function g, and when I say a function, I mean these are each functions of x, and you're going to take the derivative of that product there. How do you do that? What you do is you have the first function times the derivative of the second function plus the second function times the derivative of the first function. So the way I remember it when I see it down on paper is the first times the derivative of the second plus the second times the derivative of the first. And that's what this is saying here, there. First times the derivative of the second plus the second times the derivative of the first. That's how I remember it. Now, what would be an example of that? Okay, what if you had something like h of x equals x plus 2 over x. Well, at first you might say, that's division. That's not multiplication. But you can rewrite this, you see, as x plus 2 times 1 over x. Now I've got a function of x times a function of x, which is this. So in order to find the derivative, h prime of x, and this is exactly how I think about it when I work problems. I say first, which is x plus 2, okay, times the derivative of the second. But the problem here is that doesn't look like you know how to take the derivative of it. So you can further rewrite this, and you can say that this, let me just do it more clearly here. This is simply equal to x plus 2 times x to the negative 1. I'm just rewriting that as x to the minus 1. So if I'm taking the derivative, okay, I can say it's the first x plus 2 times the derivative of the second, which is minus 1 times x to the minus 2. Negative 1 comes out times x, and then the exponent is negative 1 minus 1, gives me negative 2. First times the derivative of the second plus the second, x to the minus 1, times the derivative of the first. Now the derivative of the first here is just going to be 1, because the derivative of this is x to the first power. The 1 comes out, and that's what I have here, okay, but then I'll have x raised to the 1 minus 1 power, because I have to do this, which is just 0, x to the 0, which again goes to 1. So the derivative of x is just 1, okay? The derivative of x is just 1. Okay, now the derivative of 2, this is just a constant. Derivative of a constant is 0, okay? So here is basically the answer. I just have to simplify it, okay? So let's go ahead and do that. Let's simplify it. What I have here is going to be negative x plus 2 over x squared. I just have the negative out front, x plus 2, put the x squared on the bottom because it's a negative exponent. Okay, and then over here, this is going to be plus 1 over x, which is this guy right here, 1 over x. Okay, so that's an example of how you would apply this guy right here. The first times the derivative of the second plus the second times the derivative of the first. Now we need to go over one more pretty important property, and that is going to be, what if you have a function of x divided by a function of g, a function of x divided by a function of x, and I take the derivative. So here I've multiplied two functions, and this is what I have to do, and here I divide two functions. What do you have to do there? Okay, well, what it is, and this is exactly how I remember it, it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That one by far is the most complicated little rule that we've learned so far. Okay, it's the most complicated little rule that we've learned so far. F divided by a function divided by a function, it's the top, the bottom one times the derivative of the top minus the top times the derivative of the bottom squared. You will use these enough where you really aren't going to have to spend too many brain cells to do it. But that's what you have here. Now, an example of that would be, what if you had t of x is equal to x to the 5th power divided by x to the 3rd power minus 2. Now, there's more than one way to skin a cat, okay? So we could break this out as x to the 5th times 1 over x to the 3rd minus 2. And I could use this formula then, this function of x times this function of x. Okay? And in fact, that's exactly how you derive this formula. Okay? If you go through that exercise, you'll get that answer down there. But we're going to use this one. And so what we're going to need to just recall then is this top function here, this is f, and this bottom function here, this is g. So as we go through it, we're going to have to remember that. So t prime of x equals the bottom, which is x to the 3rd minus 2, okay, that's the bottom, times the derivative of the top, which is 5x to the 4th. 5 comes down, x to the 5 minus 1 power gives me a 4. I use this formula right there to take the derivative of the top. So bottom times derivative of the top, that's what I've done, minus the top, which is x to the 5th. I go ahead and put parentheses around these to make it clear. Minus the top times the derivative of the bottom. Derivative of the bottom, this term is 3x squared. 3 comes down, x to the 3 minus 2 power. The derivative of a constant, this negative 2 here, is simply 0, so I don't have to do anything else. So bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. So this is the whole enchilada on the bottom. Everything squared. Okay. So what do we have on the top? T prime of x. On the top, we have to distribute the stuff in and multiply the stuff out, and hopefully it simplifies. So what we have here, 5x to the 4th times this, x to the 3rd is 5x to the 7th power. This term times this term, minus 10x to the 4th power. This term times this term. 2 times 5 is 10. You get the negative sign, x to the 4. And then finally minus this term times this term is just 3x to the 7th. Okay? And on the bottom, you've got x to the 3rd minus 2 squared. So in the end, you're going to have t prime of x. You can simplify these terms. 5x to the 7 minus 3x to the 7 is just 2x to the 7, because 5 minus 3 is 2, and you carry along your x to the 7, minus 10x to the 4th power. And on the bottom, you still have your x to the 3rd minus 2 squared. Okay. Now, you can continue simplifying that if you want. You could pull an x out, and you can try to do some other things. But in the end, that's basically the answer. How far you want to go as far as simplification, if you want to pull something out on the top, is kind of up to you and kind of up to what you want to do. But I mean, I'm perfectly happy with this. You could also expand this denominator and you'll get something big, but it's not going to really get much simpler than that. So this function is a derivative of this function. Now you can see how we're getting more and more complicated. At first, we started out with just some graphs and me explaining exactly what a derivative is, and then we had a constant line and what's the derivative of that, and then we had, well, here's basically the formula for how do you take the derivative of x raised to a power, and so on. And then we had, well, what happens if you have two functions added together, and what do you do there, and what if they're multiplied together, and what if they're divided by together? So you have a few, a handful of things that you need to know how to do. And if I have to give you one piece of advice, it would be take your time, okay? Write down everything with parentheses, keep your signs very consistent. Don't try to skip steps. Don't try to do too many things in your head. You will miss a sign, okay? And when you do, you will get the entire problem wrong, because the whole thing will be wrong when you miss a sign error somewhere. So carry your signs through, like I've got here with parentheses, and be very explicit about exactly what you mean, and then your odds of getting the problem right will go way up. Okay, I want to do a couple of quick other problems here. Just to kind of drill this stuff in. What if you have y is equal to x plus the 5th root, that's what I mean by the 5 up here, of x squared? Okay. What do I mean? How do I take the derivative of this? Well, you might look at that and say, wow, that is nothing like that is on the list. Well, go ahead and try to simplify it. Maybe you can get it into the form of something kind of like that. X plus, well, what would this be? X squared raised to the 1/5 power, maybe? Because the 5th root is just like the 1/5 power. You should remember that from your algebra, and you still have the x squared in here. So really, this is just equal to x plus, and when you have an exponent raised to an exponent, you multiply them. So this is just x to the 2/5 power. Okay? Now looky here. You have a function of x plus a function of x. Each time x is just raised to a number, so I can use this guy, and then I can calculate the derivative. So y prime, derivative of y, is equal to, what's the derivative of this first term? Well, it's simply going to be 1, because you have a 1 in the exponent. That would come down. Then you'd have x to the 1 minus 1, because I have to subtract 1 off, which would give me 0, and the whole thing would go to 1, because x to the 0 power is 1. So in the end, you have a 1. This is probably a good place to go ahead and tell you that basically anytime you see the variable by itself with nothing else going on, you're pretty much going to just take whatever number's out in front, and that's the derivative of it. And you'll see these patterns as you work problems. Plus, what's the derivative of this one? Take the exponent, put it down, 2/5 x, okay? And then what you're going to have in the exponent is 2/5 minus 1. That's in the exponent. So then this is just 1 plus 2/5 x. Now here I want to simplify this. So I'm going to have 2/5 minus. I'm going to rewrite 1 as 5 over 5 because 5 over 5 is 1. I haven't changed anything. I've just made it easier to do these fractions here. So y prime is 1 plus 2/5 x. 2 minus 5 is negative 3/5. I'm just subtracting the top, and the bottom stays the same because obviously when you're doing fractions, the bottom stays the same. 2 minus 5 is negative 3, so that would be the answer. 1 plus 2/5 x to the negative 3 over 5. So that's the answer to that problem. This is why I say you really need to work problems. I encourage you to work these problems that I'm doing here. Pause the video, go back and work them, and pull your book out, work a lot of those problems. Guarantee you'll do good on the test. What if you have something a little bit more complicated? Y is equal to x times the square root of x plus 1 over x squared times the square root of x. And how the heck do you go about doing that? Well, the first thing is you just try to get rid of all these radicals and put them in terms of exponents. So you have x times x to the 1/2, right? And then over here what you have is plus 1 over x squared times x to the 1/2, right? So to simplify this, this is just x to the 1 plus 1/2 is simply 3/2. So that's, you can just add the exponents here. 1 plus 1/2 is 3/2. And then for the next term, you'll have 1 over the same, almost the same thing. You'll have x to the, if you want to add these things up, what you really need to do is, if you really want to do this right, unless you can do it in your head, is you'll change this to a 4 over 2 times x to the 1/2. And that makes it easier to add these fractions together. See, here is x squared, but I changed it to x to the 4 over 2 because that's the same thing. 4 over 2 is 2, so I really haven't done anything to the problem. I've just changed it a little bit to make it easier. So in the end, what you'll have is x to the 3/2 plus 1 over, now I can add them, 5/2, x to the 5/2. And some of you may be able to do that in your head. 2 plus half is 2.5, and that's the same thing as 5/2. Okay? And just to totally beat it into the proper shape, that would be x to the 3/2 plus x to the negative 5/2. And what I'm going to do now is I'm going to draw kind of a little line between all this work, okay, because this is all nice, but really the problem is twofold. The first is, how do you get this into a form that you can understand? And now that we're here, what's the derivative of it? So let me go ahead and I'll go ahead and change colors. The derivative of the function y is 3/2 x, which is what I'm doing right here, 3/2 x to the 3/2 minus 1 plus negative 5/2 x to the negative 5/2 minus 1. Notice when I put this negative 5/2 there, I had a plus and then I put the negative 5/2 in parentheses. I'm just trying to keep the signs exactly straight so I never lose one of them. If you start trying to put the minus sign directly and start trying to do things in your head and be fancy, you're going to end up getting the problem wrong eventually. Okay? So when you do this fraction, you'll find out that this is equal to 3/2 x to the 1/2, 3/2 minus 1. You can write 1 as 2 over 2 if you want. 3 minus 2 is 1, so you'll get 1/2 over here. And now that I have everything clearly written, I know that I can put that minus sign there, and then I'll have 5/2 over here, x, and then this will be minus 7/2. And again, you could write this 1 as 2 over 2, and the negative 5 minus 2 on the top gives you the negative 7, and then the 2 remains on the bottom. And like I say, some of you guys might be able to do this in your head and get the negative 7/2 there. And this is the answer. Okay? So in this section of the course, we have expanded upon the basic definition of a derivative, which we said was the slope of the line tangent to a curve at a point. Okay? And we've illustrated a few rules, basically, the rules of engagement for derivatives. And this is truly, 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 truly the core of calculus, the derivative part of calculus.